Hi, my name is Mohamed Fawzy. I go by Fawzy. Today, we're going to share with you our experience over the past few years building and operating large-scale GPU clusters for AI researchers. Before going into some of the exciting technical details, let me share with you our scale journey. At Nvidia, we always had small GPU data center footprint that we used to build reference DGX architecture. My colleague Julie presented on this topic in last year at Scale. If you'd like to learn more, you can check out EOS and Selene, the supercomputers powering AI research at Nvidia, and ranked in the top 5 supercomputers in the whole world. With the introduction of LLMs in late 2021, these amazing supercomputers were not enough for the explosive compute demand required by these models. This fueled the cycle of hardware innovation, and we introduced the H100, which fueled even more innovation and increased demand on GPUs. By 2023, the few supercomputers that powered our researchers were not enough, and we needed a lot more. DGX Cloud offered a cloud-based AI supercomputer with a lot more capacity. You can see the pattern. More capacity fuel more AI innovation, which in turn fuel hardware innovation, and the cycles continue. You can see this evidently by the steep increase in both our clusters and number of GPUs after the introduction of GB200, our latest hardware architecture. You might be wondering, what is the research we're doing at Nvidia that needs all these GPUs? At Nvidia, we have a variety of research across many domains: generative AI, graphics research, simulation, robotics, and self-drivings are just few examples. Enabling all this research, innovation, and researcher productivity requires more than GPUs. It requires a computing platform that enables these needs and cope with the fast pace of innovation. This slide illustrates how our team integrate with and contribute to the broader NVIDIA ecosystem. At the center of everything is our accelerated computing platform, which drives the innovation and performance that NVIDIA is known for. As I mentioned before, the industry and ecosystem innovation through introduction of new products such as GB200 and enhancing our AI platform services drives increased GPU demand. To meet this rising demand, we focus on deploying faster, more efficient system at scale, leveraging automation, streamlining bring-up process, and world-class operational practices. With systems in place, we take on the role of operational experts. We work closely with internal researchers to understand their unique workload and needs. This helps us tailor support and infrastructure to real-world use cases, ensuring they get the performance and capability they need. Finally, we build and improve continuously. We enhance systems performance through monitoring and observability. Focusing on reliability and efficiency, we also develop tools and services that directly improve customer satisfaction and internal productivity. Ultimately, this cycle is what allows us to stay ahead in fast-moving ecosystem, supporting both our internal teams and the broader AI and research community. Today, we'd love to share with you some of the experience in operating at NVIDIA scale. In this presentation, we'll focus on 3 main areas for workload management and scheduling perspective: developer productivity, resource utilization, and operational efficiency. My colleague Bugra will go into some of the exciting technical details.
Thanks, Fawzy. Before we delve into core technical challenges, let's look at our GPU compute platform. On the top right, we see our developer productivity services, such as workload resilience and error attribution, in addition to various developer tools. Our ML workloads run on the Slurm Workload Manager, which sits on top of NVIDIA Base Command Manager for cluster management. On the top left, we see our cluster ops services, such as health checks, break fix automation, as well as bring up automation and data migration services. We rely on Kubernetes for running some of these add-on services, but our ML workloads run on the PCM Slurm stack. On the rightmost, we see our resource governance tooling, which is used for cluster onboarding, account and allocation management, forecasting, among other things. And on the leftmost, we see our core observability stack, metrics, logs, and monitoring. Let's dive into one of the key problems around researcher productivity, which is fair sharing. Fair sharing provides resource guarantees based on agreed-upon quotas. It is critical for researcher productivity because it avoids workload starvation and resource hoarding, and it can reduce wait times. To support Nvidia's organizational scale, we rely on 4 levels of fair sharing. The first is account-level fair sharing. We organize users under a hierarchy of accounts for resource governance purposes, and these accounts have quotas associated with them, and we share resources fairly among these accounts based on those quotas. The second is over-quota fairness. When not all accounts have demand, we share excess resources among the accounts that have demand proportional to their quotas. The third is user-level fair sharing. Within an account, we share resources fairly across the users that have demand. And the final one is workload-level fairness. When we have multiple long-running workloads, and these workloads could run for days, we would like to provide fairness at smaller timescales. With this understanding, let's look at some of the key scheduling considerations in the context of fairness. The scheduler provides fairness by balancing resource usage based on account quotas. There are 2 main ways to do this. One is called instantaneous and the other is historical usage-based. The instantaneous fairness looks at only the current usage when computing fairness and making scheduling decisions. This is typical in Kubernetes batch schedulers. Historical usage-based fairness, on the other hand, looks at past usage data, optionally applies a time decay, and then uses the aggregated historical usage to make these decisions. In our environment, historical usage-based fairness has multiple advantages. For instance, accounts with small quotas can make use of over-quota resources without instantly getting preempted. At the same time, the fairness is still maintained when amortized over time. The configurable time decay enables us to make trade-offs between 2 extremes. With no decay, we have GPU hours-based fairness, which favors accounts with small quotas and sporadic usage, whereas with fast decay, we get closer to instantaneous fairness, which favors accounts with large quotas and consistent usage. Later in the presentation, we'll look at how we use simulations to make informed decisions when it comes to configurations like this. Now let's look at workload resilience, which refers to our ability to reliably and efficiently run workloads without attention from the users. There are 2 reasons why this is a challenge, especially for large and long-running jobs. First is workload fairness. When we have multiple workloads that do not fit into the quota, we need to provide time sharing among them. The second is infrastructure unreliability, which we will cover shortly. There are multiple ways to provide time sharing. One is to use a max running time for workloads, after which they have to be resubmitted for schedule. While this works as a solution, it creates unnecessary overheads when there are no competing jobs for resources. And this is because ML jobs need to perform various initialization stages before they can get to do useful work. An alternative approach we are now adopting for our clusters is to have a minimum guaranteed running time before we enable fairness-based preemptions for jobs. This approach doesn't cause unnecessary overheads when there is no contention. And later in the presentation, we'll talk about its positive impacts on cluster utilization. Another reason jobs, especially large jobs, might see interruptions is infrastructure unreliability. For instance, low mean time between failures, either due to hardware problems or problems with infrastructure services, can cause large jobs to fail frequently. To address this problem, we rely on a fault isolation and workload lifecycle management service that sits on top of the scheduler. This service is responsible for identifying infrastructure failures and resubmitting jobs automatically when such failures are detected. We also rely on a comprehensive set of health checks to help isolate bad nodes and break fix automation to bring those nodes back into the fleet as soon as possible to keep the availability high. For large-scale LLM training, we have seen this resilience approach reduce downtime by 6 times and interruptions by 5 times. Even after providing fairness and resilience, there is still a big challenge with researcher productivity. Researchers need a lot more resources than what's available. I'll now hand off to Vikas, and he's going to cover how we address this problem.
Thanks, Bugra. Hello, everyone. Over the past few years, we have witnessed massive investments and exponential growth in GPU capacity. More importantly, the demand has continued to exceed supply by an order of magnitude. Given the significant shortfall in capacity, effective use of available GPU resources is critical to maximize researcher productivity. One of the key metrics we use to measure resource utilization is cluster occupancy. We define cluster occupancy as resources allocated to user jobs divided by the total available GPUs in the cluster, excluding any GPUs that are down for maintenance or repairs. Improving this metric reduces the idle GPUs, which in turn reduces the wait time for the jobs and also maximizes the return on our infrastructure investments. We operate our cluster consistently at around 95% occupancy. This is achieved primarily by running them as large multi-tenant shared resource pools. This model allows for temporal resource overuse to run jobs that can be larger than an account's share or when there is low demand from other tenants in the cluster. To improve cluster occupancy, we first need to attribute the key reasons for occupancy loss. Here we identify 5 major reasons for the occupancy loss and their relative impact. Among these, GPU collection and node fragmentation are typically the largest contributors. This is primarily due to complexity of bin packing diverse workload, ranging from jobs needing single GPU, thousands of GPUs, while also adhering to their fairness constraints. GPU collection refers to scheduling process where GPUs are held idle in collecting state until sufficient number of them are available to meet the resource requirements of the job with the highest priority. This penalty increases with the job size and with the minimum guaranteed runtime. For example, when jobs are allowed to run uninterrupted for 4 hours, scheduler needs to wait for proportional amount of time to collect resources for the highest priority job. For long-running jobs, removing the unnecessary interruptions due to hard wall time constraints reduces the number of times these jobs need to be rescheduled, effectively reducing the collection penalty. To ensure fairness, a job gets minimum runtime guarantee, after which it becomes preemptible. Another technique we use to reduce collection penalty is backfill scheduling, which enables scheduling jobs onto collected idle GPUs as long as the backfill jobs are expected to complete before the estimated start time for the highest priority job. Now let's look at the other side of the spectrum, where partial node jobs can cause some of the GPUs on a node to remain idle. One of the key factors of node fragmentation is job shape, where disproportionate amount of non-GPU resources are requested by the job. For example, here jobs request 2 times more CPU per node than GPUs, causing half of the GPUs on the node to remain idle and unallocatable. Job runtime variance reduces bin packing effectiveness. When a node is available for a limited amount of time and some of the partial node jobs complete early, scheduler cannot allocate free GPUs to other partial node jobs when these resources are available for less than minimum guaranteed runtime. To reduce this penalty, we are moving towards proportional resource allocation to guarantee that all the GPUs on a node can be allocated with sufficient CPU and memory. Additionally, separating the node pool for partial node jobs removes the time constraint for the scheduler, enabling it to effectively bin pack GPUs on the node as they become available. Scheduling inefficiency can in itself be a full presentation topic. Key point to highlight here, besides bin packing effectiveness of the scheduling algorithm, is its performance. When the scheduler is not able to keep up and the node allocation rate falls below the rate at which the node becomes available, we see occupancy loss. We support resource reservation for special need use cases, and since these resources are not shared, any downtime for its tenant leads to occupancy loss. We minimize the overall use of reservations to keep this loss in check. While at macro level, demand is an order of magnitude more than available capacity, in some of our clusters, we occasionally observe low demand around conferences, weekends, and holidays. We periodically reevaluate demand per account and adjust their shares to manage demand. While maximizing occupancy is highly valuable, it comes with trade-offs involving wait time, performance, goodput, and more. With that, I will hand it off to Vipin, who will walk us through how we use simulations to evaluate and make informed decisions involving these trade-offs.
Thanks, Vikas. All right, let's shift our focus now on operational experience we've gained managing these large GPU clusters. As we have scaled, we have encountered some significant challenges, particularly when it comes to safe deployment of scheduling policies and releases. One of the core complexities stems from the sheer diversity we are dealing with. Think about it. We have a wide range of GPU hardware, various CSP environments, multiple scheduler versions, and an incredible diverse set of workloads. This variability naturally leads to huge diversity in scheduling policies and configurations. And that's where things get tricky. Each combination of these factors can behave differently. What works flawlessly in one environment might cause unexpected issues on another. This diversity makes testing and validation new scheduling policies or releases incredibly challenging. And it's something we've had to develop robust strategies to address. We will be diving into these strategies next and how we ensure safe and reliable deployments. With these challenges posted by diversity, we have developed a streamlined strategy for safe deployment. This strategy centers on three-stage process. First, we simulate diverse scenarios to anticipate potential issues. Next, we compare and improve based on simulation results, refining our configurations. And finally, we deploy the change with strong focus on monitoring and rapid rollback capabilities. This process is heavily reliant on our simulation environment, which we discuss next. Our simulator is equipped with several critical capabilities that make it a very important tool for safe deployment. We can achieve a realistic replay of job traces, mirroring the actual workloads from the production clusters. It also handles fair share scenarios, ensuring we maintain desired resource distribution. We can simulate node availability, including the impact of node failures and reservations. And to accelerate our testing, the simulator offers simulation speeds of up to 24 times. The interactive environment allows us to make real-time adjustments and observe their effects immediately. And finally, we have flexibility to use synthetic job traces and perform patch testing. These features collectively provide a comprehensive platform for validating changes before they even make it to the production. The simulator workflow is designed to facilitate rapid evaluation of scheduler configuration. It begins with gathering of real or generation of synthetic job traces. We then replay these traces within the simulator. This allows us to apply configuration changes, custom patches, and subsequently analyze the outcomes. This iterative process allows quick identification of issues and tuning of any configurations. We emphasize data-driven decision by running comprehensive simulation for each potential cluster configuration. Our simulator demonstrates high fidelity in replicating production metrics given the same workload, which gives us high confidence in the simulation results. To illustrate the effectiveness of this approach, consider this example. By running simulations for various cluster configuration, we identified a configuration that would have significantly increased job wait times if deployed in production. This early detection, facilitated by our simulator, allowed us to avoid potential disruptive scenario. Simulation allows us to catch potential issues early and make adjustments before they even impact the production. With this now, I will hand over to Fawzy to do the rest of the presentation.
We're entering the next era of generative AI, where we are seeing applications in many fields: medical, self-driving, and many more applications and research areas. In this era, we'll see models that are able to reason with much higher accuracy and intelligence, which requires a much longer chain of thoughts. This will drive exponential demand for compute, particularly for inferencing. At Nvidia, we'll continue to scale this compute demand through our DGX cloud infrastructure. DGX cloud infrastructure not only powers our internal AI compute demand, but offers external services, globally available, scalable compute. I'm proud of what the team accomplished with the recent challenges. With GB200 architecture, we're looking for some exciting challenges, such as enable further research productivity by improving our scheduling techniques and making it more data aware. With our explosive scale, resource efficiency becomes even more important. We want to continue to drive operational excellence at scale to enable us to move fast. We're looking forward to bring these learnings to the broader community through our DGX Cloud Create product offerings, as well as open sourcing some of these innovations. Thanks for listening, and I hope you enjoyed the talk.